Right now, on a mountaintop in the Chilean Andes, a camera the size of a small car is taking a new photograph of the entire visible universe roughly every 40 seconds. No digital camera this large has ever been built. No single instrument has ever mapped this much sky this fast in the history of astronomy. No observatory has ever thrown away more data on purpose because it was too busy finding something more important to keep. It is not a telescope anymore, not in the old sense of the word. It is an early warning system for the entire solar system running 24 hours a day. And it only just switched on. Stay with me, because in its very first images, this machine found something that a room full of professional astronomers is still working through right now in 2026. If you're new here, this channel breaks down real space missions in plain language. No filler, no fiction. So if that sounds like your thing, hit subscribe. It's free. Let us go back to the beginning. The observatory is named after Vera Rubin, an American astronomer who, in the 1970s, measured how fast stars orbit at the outer edges of spiral galaxies, and found something that made no sense under the physics anyone had at the time. Those outer stars were moving far too fast to be held in orbit by the visible mass of their galaxies alone. Fast enough that by the standard laws of gravity, the galaxies should have been flying apart. They weren't. Rubin's careful, repeated measurements became some of the strongest evidence that most of the mass in the universe isn't visible at all. What astronomers now call dark matter, a substance that has never been directly seen, only inferred from its gravitational fingerprints. It was reasonable at the time for scientists to be skeptical of that idea. Extraordinary claims about invisible mass demanded extraordinary evidence, and Rubin spent years accumulating exactly that, one galaxy at a time, until the pattern became impossible to dismiss. She did this work largely without the institutional recognition male astronomers of her era received automatically. And she was denied access to some observatories simply because of her gender, a detail that makes naming humanity's most ambitious sky mapping machine after her feel less like a courtesy and more like a correction. Decades later, the observatory built to carry her name was designed to chase both of the universe's biggest unsolved mysteries at once: dark matter and its stranger cousin, dark energy, the unexplained force that appears to be accelerating the expansion of the universe itself. Together, those two invisible components make up roughly 95% of everything that exists. Read that again. Everything we can see, touch, and build, stars, planets, people, is a rounding error. To go after that, engineers built something almost absurd in scale. At the summit of Cherepon, more than 5,000 FT up in Chile, sits the 8-4 Survey telescope. Its primary mirror cast at the University of Arizona back in 2007 and shipped south over the following decade. Bolted to it is the LSST camera, a 3,200 megapixel imaging system built by teams at SLAC National Accelerator Laboratory, the largest digital camera ever constructed for any purpose anywhere. A single full-resolution image from that camera is so large that it would take about 400 ultra-high-definition television screens arranged edge to edge just to display one photograph at its true size. This is not a metaphor. This is the literal geometry of one snapshot. The project moved through its milestones methodically. A test campaign with a smaller commissioning camera beginning in October 2024, the full 300 to 200 megapixel camera installed in April 2025. And on June 23, 2025, the observatory finally showed the world what it could do in an event called simply First Look. Those numbers and dates matter because everything that follows in this story happened inside that window barely more than a year, start to finish, of a project that had been 30 years in the making. The engineering behind that camera is worth sitting with for a moment because the specific design choices explain everything that came afterward. Most telescopes trade off field of view against sensitivity. You can see a small patch of sky in exquisite detail, or a huge swath of sky in comparatively coarse resolution, but rarely both at once. Rubin's camera was built specifically to break that trade-off, combining an unusually wide 9.5-degree field of view, roughly 45 times the apparent size of the full moon, with sensitivity fine enough to catch objects fainter than almost anything a ground-based survey had reliably detected before. That combination is precisely why the camera can complete an image every 40 seconds and still resolve individual faint galaxies inside it. It isn't choosing between breadth and depth. It was engineered to refuse that choice entirely. Every part of the observatory's design, from the mountain it sits on to the rapid slew mount that lets the whole telescope structure swing to a new target and settle, almost immediately was built around one governing requirement: move fast, see wide, and never blink. The first look images themselves were by any honest measure staggering. One released composite stacked 698 separate exposures, taken over just 7 hours, revealing the Trifid and Lagoon Nebulae, vast glowing clouds of star-forming gas several thousand light-years away in colors and structural detail no previous image had captured. A wider mosaic of the Virgo Cluster, a dense knot of galaxies, contains something on the order of 10 million individual galaxies in a single release, the vast majority of which had never been cataloged or studied by anyone before that morning. Here's where it gets worse. For the old way of doing astronomy, nearly all previous ground-based sky surveys operated by picking specific targets and studying them carefully, one at a time, over months or years. Rubin doesn't do that. Rubin photographs everything everywhere on a repeating cycle, whether or not anyone asked it to. Then came the number that actually stopped people. During the observatory's very first test observations, a window of just over 10 hours of pointing the finished camera at the sky before the survey had even officially begun, Rubin detected 294 previously unknown asteroids in our own solar system, 7 of which were classified as near-Earth objects. Sit with that for a second. Every professional and amateur observatory on the planet combined finds somewhere in the range of 2,000 to 3,000 new asteroids in an entire year of dedicated searching. Rubin matched a meaningful fraction of a full year's global asteroid hunting output in less time than most people spend at their day job. This is not an incremental improvement. Rubin is little better than the old telescopes. This is proof that the entire previous era of ground-based sky surveying became obsolete somewhere in the space of a single overnight test run, and most of the world didn't notice because it happened quietly, framed as a technical rehearsal rather than a headline. Put it another way. Imagine every asteroid hunting telescope on the planet as a team of night shift security guards, each one scanning their own small patch of a vast dark parking lot, radioing in anything unusual, maybe once or twice a week. Rubin doesn't join that team. Rubin replaces the entire parking lot with floodlights and installs a camera on every single lamppost simultaneously. And it did this so effectively that during its very first test shift, it found more previously invisible objects than most of those guards would report in months. Here's where it gets worse for anyone still relying on the old approach. This wasn't even the finished product operating at full capacity. This was the camera's first real look at the sky, running well below what the completed 10-year survey is designed to sustain night after night. It didn't stop there. Over the following weeks, as engineers ran the system through a longer stretch of early optimization surveys, roughly a month and a half of observing before the formal 10-year mission had even started, that asteroid count kept climbing, eventually surpassing 11,000 newly discovered objects, including 33 near-Earth objects and 380 trans-Neptunian objects out in the frozen dark beyond Neptune's orbit. Read that again. 33 previously unknown objects on trajectories that bring them close to Earth's own orbital neighborhood, found essentially as a side effect of the observatory clearing its throat before the real survey began. What most people are not seeing in the headlines about beautiful first images is that the actual scientific event wasn't the pretty pictures at all. It was the asteroid catalog quietly growing in the background of every single one of them. Here is where this stops being an abstract story about pretty nebulae and starts being a story about Earth specifically. Every near-Earth object Rubin finds is added to a global tracking catalog maintained by the Minor Planet Center, the same clearinghouse that space agencies around the world consult when assessing whether any given asteroid poses a real long-term impact risk. For decades, planetary defense has been limited by a simple, unglamorous bottleneck. Telescopes can only warn us about objects they've actually found, and the smaller, darker near-Earth objects, the ones large enough to devastate a city, but too small and dim for most existing sky surveys to catch reliably, have always been the hardest to detect until they're uncomfortably close. A machine that finds dozens of them as an incidental byproduct of testing its cameras is not just an astronomy story. It's a direct upgrade to the actual early warning infrastructure protecting the planet, running quietly in the background of a press conference about nebula photographs. This is where the abstraction ends completely. Every one of us lives on a planet that has been struck by large objects from space before repeatedly across its geological history. And the only real defense against that happening again is knowing an object is coming with enough lead time to do something about it. That lead time has always been the bottleneck, not the physics of deflecting an asteroid once it's found, but simply finding it early enough in the first place. A survey that adds 33 new near-Earth objects to the global catalog before its official mission has even begun is not a curiosity buried in a press release. It is 33 fewer unknowns hanging over every future year of human civilization. But getting to that press conference at all nearly didn't happen on schedule. And the story of the final stretch is genuinely tense. In May 2025, with the first look event just weeks away and a room full of government officials, journalists, and scientists already expecting a public unveiling, the observatory's engineering team hit a serious problem. The camera itself was overheating, not a cosmetic glitch, not a software hiccup. A physical thermal management issue inside the most expensive, most complex digital imaging system ever built, discovered at the worst possible moment, with a hard public deadline bearing down and no simple way to swap in a spare. Fatigued teams gathered in the observatory's control room in Sarapon, running diagnostics late into the night, trying to isolate exactly which component was running hot and why, knowing that the camera's 3,200 megapixels of imaging sensors are cooled to extraordinarily precise, extremely cold operating temperatures, and that even small deviations from those thresholds can degrade image quality or risk damaging the sensor array itself. There was no backup camera. There was no factory across town that could ship a replacement overnight. Whatever fix they found had to work on the only one that existed, installed on a mountain in Chile, with the world's press already booking flights to attend the unveiling. Consider the actual stakes of getting this wrong. The LSST camera had taken years to design, build, and test before it was ever shipped south to Chile and installed on the telescope in April 2025. There was no version 2 waiting in a lab somewhere, no contingency camera sitting in storage. If the thermal problem couldn't be isolated and corrected before the scheduled event, the choices facing the team were all bad ones. Postpone a nationally announced unveiling with government officials already scheduled to attend or reveal images captured by a camera operating outside its intended specifications, risking exactly the kind of visible defect or noise pattern that would undercut public confidence in a project 3 decades in the making. On the very day it introduced itself to the world, every hour the team spent chasing the fault was an hour closer to one of those 2 outcomes becoming unavoidable. They found it in time. The engineering team traced and corrected the thermal issue, brought the camera back within its operating tolerances, and on June 23, 2025, first look happened exactly as planned, generating the headlines and the nebula photographs that made global news that week. Think about what that near miss actually means, though, because the drama didn't end there. Even after first look succeeded publicly, the observatory still wasn't ready to begin its actual 10-year mission. Officials had originally hoped the full legacy survey of space and time, the LSST, the real decade-long scientific campaign this entire project exists to run, would begin in early 2026. It didn't. According to Jellico Evazich, the astronomer serving as head of LSST, the decision to formally begin came only after, in his words, a careful operational review covering image quality, effective survey speed, system uptime, and reliability and calibration accuracy. A months-so-long stretch of quiet, unglamorous verification work, invisible to the public, that delayed the actual start of the flagship survey by roughly half a year past the original target. No single dramatic failure caused that delay, just the accumulated weight of making absolutely certain that a machine designed to run essentially unattended every clear night for 10 straight years would not need to be fundamentally reworked 6 months into its life. Here's what is happening right now in 2026. On February 24th, 2026, the observatory crossed a milestone almost nobody outside the astronomy community noticed: the launch of its real-time discovery alert system, which, on its very first night of full operation, flagged 800,000 separate transient events, objects that had moved, brightened, faded, or otherwise changed since the previous observation, and pushed that information out automatically to research teams and automated software systems around the entire planet within minutes. Then, on the night of June 29th into June 30th, 2026, the observatory formally began the legacy survey of space and time itself. The actual 10-year mission this entire decades-long project was built to run. The camera is now capturing a new detailed image of the sky roughly every 40 seconds, completing a full pass of the visible southern sky every few nights, generating more raw astronomical data in its first year alone than every other optical observatory on Earth combined has produced across their entire operating histories. Current projections, based on the survey's expected 10-year scope, put the eventual total haul at something like 20 billion galaxies, 17 billion individual stars, 10 million supernova explosions, and roughly 6 million solar system objects, asteroids, comets, and other bodies orbiting our own sun, all cataloged, tracked, and made available to scientists worldwide. This is not a plan for the future. As you are hearing this on a clear night in Chile, it is already happening. There's also a quieter, less cinematic present-day reality worth naming directly. Reaching this point took longer than anyone originally hoped, and the mission's own leadership has been candid about why. Prior to the formal survey start, alerts had already been streaming to research teams since late February, but only in a limited, ramped-up form. Because the full alert system depends on reference template images that themselves take time and careful calibration to build. New solar system discoveries were for months being reported to the Minor Planet Center on an ad hoc basis rather than through a fully automated pipeline, precisely because the team refused to switch on the finished system before it had been checked, rechecked, and checked again. That is not a failure. That is what responsible operation of a machine this consequential actually looks like from the inside, even when it means the public-facing story arrives months later than the original announcement suggested it would. And there is one date on the calendar that isn't a projection or an estimate. It's a scheduled certainty built directly into the mission's own operating plan. Rubin's science team has publicly targeted the end of June 2028 for the release of Data Release 1, known as DR1, the survey's first full annual dataset built from an entire year of continuous observations of the changing sky. That date isn't a guess dressed up as a headline. It is the direct calculated consequence of the survey having formally begun in late June 2026, plus the roughly year-long processing pipeline the Rubin data system requires to turn raw images into a scientifically usable, fully calibrated catalog. 20 billion galaxies, 6 million solar system objects, all of it converging toward a single lock-it-in release window, less than 2 years from the moment this survey first opened its eye on the sky, arriving whether or not anyone is paying attention when it does. Now, the honest part, because this story doesn't come with a clean bow on it, Rubin was built with two central scientific mysteries in its sights: dark matter and dark energy. And after everything described so far, neither one is remotely close to being solved. The leading explanation for dark matter remains some undiscovered particle that barely interacts with ordinary matter except through gravity, a hypothesis that decades of dedicated particle detector experiments have still failed to confirm directly. A competing line of thought holds that our understanding of gravity itself might simply be incomplete at galactic scales, meaning there may be no exotic invisible particle at all, just a modification to Einstein's equations that nobody has yet gotten exactly right. Dark energy is arguably murkier still. It could be a genuine constant property woven into the fabric of empty space itself. Or it could be evidence that the equations cosmologists have used for a century need real revision. Rubin's 10 years of repeated wide-field imaging are specifically designed to gather the statistical evidence that might finally distinguish between these competing pictures. But as of today in 2026, that evidence is still years away from being complete. And any scientist telling you they already know which explanation wins is telling you more than the data currently supports. What most people are not seeing is that this uncertainty isn't a weakness in the project's pitch. It's the entire reason the project exists. If dark matter and dark energy were already understood, there would be no 10-year survey to build in the first place. The honest position shared by the researchers actually running this mission is that Rubin was designed specifically because nobody currently knows which of these competing explanations is correct. And the only way to find out is to gather more data than any previous instrument has been capable of collecting. Step back from the asteroid counts and the overheating camera and the 400 television-sized photographs, and there's a larger pattern worth noticing. Every leap forward in how humanity sees the universe has followed roughly the same shape. Build an instrument good enough to look properly for the first time, point it at the sky, and discover that the universe was doing something all along that nobody had the tools to notice before. Rubin didn't set out to find 11,000 new asteroids in 6 weeks. It set out to build a systematic repeating map of the entire visible sky. And the asteroids, the supernovae, the changing brightness of distant stars, all of it simply fell out of doing that one job well enough. That is the actual mechanism by which most real scientific progress happens. Not a single genius insight arriving out of nowhere, but a tool built patiently over 3 decades, pointed at a question its builders were honest enough to admit they couldn't yet answer, catching everything else in the process, almost as a courtesy. Think about what that means for how we should judge a project like this one. It would be easy to measure Rubin purely by whether it eventually confirms dark matter or rules it out or delivers some other single headline ready verdict. But the more honest measure is already visible in everything that happened before the real mission even started in the 10-hour test run that outpaced a year of global asteroid hunting in the 11,000 objects found almost by accident during system checkout. A tool built well enough finds things nobody was specifically looking for simply because it was built to look at everything all the time without preference or fatigue. That is not a lesser form of discovery than a single dramatic breakthrough. In the long run, it may be the more reliable one. There's a particular kind of vertigo in imagining that camera alone on its mountain, doing this every clear night, whether or not a single human being is awake to watch. Every 40 seconds, a shutter closes over a portion of sky that has never been photographed at this resolution before. And somewhere in that image almost certainly sits something nobody has named yet. An asteroid on a slow, silent path nobody has calculated. A star flickering in a pattern nobody has explained. A supernova mid-explosion. Its light having traveled across most of cosmic history just to land for one exposure on a sensor built by human hands on a mountaintop in Chile. The universe does not pause and wait to be observed. It has been doing all of this in the dark for billions of years, regardless of whether anyone was watching. Rubin is simply the first instrument patient enough and wide-eyed enough to catch nearly all of it at once. Somewhere in the archive already sits an image containing a supernova that no human eye has looked at yet. Its light crossing the gap between 2 galaxies for longer than our species has existed. arriving on a mountaintop in Chile at almost precisely the moment someone finally built something capable of noticing. So here's everything in one breath. Named for an astronomer whose careful measurements of galaxy rotation gave us the first strong evidence for dark matter, the Vera Rubin Observatory spent 3 decades in construction before revealing its first images on June 23, 2025. Nebula, galaxy clusters, and almost as an afterthought, over 2,000 new asteroids found in a single 10-hour test run. A last-minute camera overheating crisis nearly derailed that unveiling weeks beforehand, and months of careful system verification pushed the start of the real 10-year survey back from an early 2026 target to late June 2026. Since then, the observatory has launched a real-time alert system flagging hundreds of thousands of changes in the sky every night, begun the legacy survey of space and time in earnest, and set its sights on a scheduled first full data release by the end of June 2028. All while the fundamental questions of dark matter and dark energy that inspired the entire project remain genuinely, honestly unsolved. If you want to be there for what Rubin finds next, because DR1 alone is expected to reshape entire subfields of astronomy, hit subscribe and turn on notifications, since I'll be covering the major releases as they land. One question before you go. Given the choice, would you rather see Rubin find a definitive evidence for dark matter or proof that our whole model of gravity needs to be rewritten instead? Let me know in the comments.